Hello everyone, so this is the first tutorial about the plasticity in the Ansys software and how it could be done, how it could be possible to simulate a rolling experiment. Actually this is really easy and I'll try to show you how it could be done using Workbench. Well, first of all, this is my first tutorial and don't judge myself too much. And also sorry for the sound because I don't have microphone now. I just use the laptop microphone. So first of all, the problem is about rolling and plastical deformation of metals. This is common instructions how we simulate it, and we will try to make almost the same geometry. However, you can see here there is a symmetrical axis, so we will use this condition to make our simulation easier. The first that you should know about this problem is that we need to use nonlinear properties of material, especially plasticity. So usually when you work with elastic materials and elastic properties, you work in this region, the blue one. This is a stress-strain curve, and when you use just Young modulus and Poisson ratio, so you can only simulate these properties. But for plastic properties, plastic deformation, we need to put also in our analysis more complicated properties of material, such plasticity and this plastic region. Of course, we would not work with fracturing, but this part is of our interest. So let's start simulating. This is common Workbench window, and we will prepare our simulation. First of all, we need geometry. I usually work with standalone parts. I don't like just analysis and to put everything inside the analysis. Also, we need static structure. Why static? Why not transient? Well, usually dynamic problems are simulated with transient analysis, transient structure, but in this analysis we don't need inertial effects, and with inertial effects our analysis become really heavy and complicated for simulation, especially for simulation time. We don't need this. We are okay about just static analysis. So geometry. This problem is 2D. Also here, this problem is 2D, so we can simulate just 2D geometry. And let's start preparing our geometry. We need to make a roller and the specimen, the half of specimen. Let's wait a little bit until the window starts. Yes, here it is. So x, y plane, units millimeter, and let's start with the roller. I need circle, something like this. Also, it is enough for roller. We will create surface from sketch. So this is our sketch, and we'll generate the surface. Okay. The next step is to create specimen. We need to create new sketch in the same extrude plane, and then click on sketch 2, sketching, and create rectangle. So we need to create a rectangle a little bit larger than than this size, for example from here. So this is initial point of contact between roller and specimen. Sketch 2, tools, concept, surface from sketches. Generate. Okay, let's check what we have. We have two parts, one surface body that is the roller and the second body that is our specimen. That's enough for the geometry. Let's close the window. We need to move our geometry to our analysis like this, and also we need to create the plasticity properties of our material. Let's go to engineering data. Here, let's open engineering data sources on the top of your window, and you need to find general nonlinear materials. Here we have nonlinear materials. We need, for example, aluminum alloy nonlinear. This part means that this material has nonlinear properties. Click on the plus, and if you have the sign of the book here, then you just edit your aluminum nonlinear to your analysis. Let's close engineering data sources and let's check what we have here. We have structural steel as a just standard material. It's linear. It has only isotropic elasticity here. But here for aluminum alloy, we have not only isotropic elasticity with Young modulus and Poisson's ratio, but also bilinear isotropic hardening. And as you can see here, we have stress-strain curve for bilinear isotropic hardening. This is the example of such stress-strain curve for aluminum. Here, two parameters. Yield strength, it's the first point when you change linear deformation to just elastic deformation to plasticity. And tangent modulus, it's tangent of the angle between horizontal axis and the plastic axis, plastic curve. Okay, so we have plastic properties. Now we can go to the simulation. Let's start to create our model. Let's wait some time. This laptop is not so powerful, so I'll try to make the most light simulation just to demonstrate you how it could be done. So here we have the almost lowered window for our simulation. Let's wait for some more time. Okay. So this is our simulation. As you can see, we have geometry here, and first of all we need to put the appropriate properties for each body. The first body, roller, will be flexible and structural steel, so without any changes. Our specimen should be aluminum alloy nonlinear. In the material part assignment, you should put aluminum alloy nonlinear and check that you have nonlinear effects. Yes, this needs to be also turned on. Geometry should be with the property of plane strain, because for the plane stress you will work with plates. For the plane strain you will work with 2D plane problems. It's two different simulations. Okay, for the geometry is enough. Then we need to add symmetry region. As I said, we are using this property to make the easier simulation. Insert, so you click by your right button on the symmetry, insert symmetry region, and before this I choose this line, this edge of the specimen, the symmetry edge, and edit symmetry region. Here type symmetric, symmetry normal, not X but Y or Y. Connections. Connections are between the roller and two edges of our, or maybe even one edge, but I will put two. So, contact frictionless. We don't need friction in this simulation because it's much more difficult to simulate according to that. It's not so important in this tutorial. So the contact edge will be this edge of the roller, and the target edges will be here, these two edges of the specimen. Frictionless and all other properties are as usual. Mesh. Let's generate mesh and see how it looks. Well, it's just two elements for the specimen, but I think it's okay, just for the presentation. As I said, this is just tutorial for demonstration how it could be done. At the end of the tutorial I will describe all properties that could be added to make more complicated simulation. So, analysis. First of all, we need to fix our roller. Let's make fixed support for this face. Okay. And also we need to move our specimen through the roller. So let's, for example, take this edge and create displacement. So let's see, we have x-axis and we need to move it in opposite direction, so it will be minus. And as we see, it's about 45, yes, 45 millimeters. It's just my ideas. It's not, you could put anything here. So also in the analysis settings we need turn on auto stepping, turn on, defined by time. Let's make initial time step like this, minimal like this, and maximum like this. You can put here some other numbers as you want, but I think this would be okay. Also we need to turn large deflection on. This is a must, really important. Inertia relief is off because we don't study inertia in this problem. It's quasi-static problem and it's okay without inertia. As a result, we need just deformation, equivalent strains, equivalent stress. Also, I want to see plastic strains, and let's also in the nonlinear controls I will turn force convergence on and displacement convergence on. So let's solve. Let's see the solver output for force convergence and watch how our solution is done. So the first steps are really smooth, but after some sub-steps we have convergence for the contact problem. So this is really nice convergence. As you can see, just some 2 or 3 sub-steps, and then substep is converged. It's really nice for the simulation. The simulation time is 1 second, and we are almost at the middle of our simulation. It's really fast because, first of all, it's 2D problem. It's frictionless according to contact properties. And the mesh is really is of course it's not so good, but who cares? Now it's just simulation. It's not the real practical problem. So until it's done, I will try to also add some tips on the more complicated opportunities for such simulations. For 3D problems, for more complicated shapes, without symmetry, without anything else, the steps are the same. You just need to create a roller and specimen. You just need to create nonlinear properties for specimen. Also, you need to create contacts. Of course, usually in real situation they are with friction, but you could use it without friction. You should try to compare properties, results for friction and frictionless contact, and you'll see that for the specimen it's not so important. Also, boundary conditions, and of course here you should put nonlinear large deflection, and just fix your rollers and move your specimen through the rollers. So let's see. So as you can see, the displacement minus 45 is not enough for the total deformation, but the analysis is okay. So let's create the animation more smooth, and let's see how it's done. As you can see, the specimen moves through the roller. We have plastic deformation, and at the end of the deformation it's not really nice because this is the axis of symmetry and this part of specimen moves through this axis. It's not real, but as I said, it's just simulation, just for tutorial to demonstrate how it could be done. Let's see the plastic strain. This is the most important and interesting. As you can see, plasticity is concentrated on the top of the body. Of course, for such mesh, it's everywhere, it's very rude, and results are not so accurate, but and also here the maximum is because of the bending of the end of our specimen. So as I said, and I will say it again, this is just simulation for the tutorial. I hope it was demonstrative and you will make the same. And if you have any questions, just write me back in the comments below the video. And I hope it was nice. See you next time. Bye.